This is the third section in the Methods in Calculus chapter, and here we're going to be looking at differentiating inverse trig functions. Okay, now some of these methods are very similar to the differentiating hyperbolic functions, which is chapter 6. I think it's section 6.4. So you might want to take a look at that video and just compare the methods. They're very similar. Yes, I'll put a link in the description so you can click on that as well. And what we're going to use, we'll use a method which is called implicit differentiation. So implicit differentiation. And basically implicit differentiation is normally we're so used to doing dy dx. Yeah, we can find, oh well, that's the same as 1 over dx dy. Yeah, they're like reciprocals of each other. That's basically implicit differentiation. So we can get something where we have some, let's say x equals a function of y, and we differentiate that, and dx dy or dy dx is going to equal 1 over that function of y differentiated. So that's basically dx dy. We're going to use that to help us differentiate these inverse trig functions. Right, so the first one, we want to show that when we differentiate arc sine x, we get 1 over 1 minus x squared. So the first thing is we want to write y equals arc sine x. We need something like this rather than just an expression floating around on its own. And then the first thing that we do is that we do sine to both sides. So I'll have sine y equals x. Then we're going to use implicit differentiation for both sides. So remember, with implicit differentiation, whenever you differentiate a y term, you put dy dx after it. And if it's a mixture of x and y, you use the product rule. So again, I can put a link to the pure to implicit differentiation, but the rule is whenever you differentiate a y term, put dy dx after it. That's just to show you've differentiated a y term as if it were an x term. So sine y will become cos y, but we write dy dx because we're working out dy dx, not dx dy. Then if you differentiate x, we get 1. So that'll be our step. We want to work out what dy dx is, so we're going to make dy dx the subject. So dy dx will equal, well, it's going to be 1 over cos y. So here we can use the identity for this bottom part here, because we know that sine squared y plus cos squared y is 1. So if we rearrange that, we'll get cos squared y is equivalent to 1 minus sine squared y. So if we square root both sides, we will get dy dx equals 1 over the square root of 1 minus sine squared y. But what did we have up here? Sine y equals x. That means this can be replaced with x squared. So we will have, wrong colour, we will have dy dx equals 1 over the square root of 1 minus x squared. And we've sort of proved it. We've shown that if we differentiate with respect to x, arc sine x, using this implicit differentiation, we've shown that it's 1 over 1 minus x squared. Okay, using this method of implicit differentiation. Okay, so we're given that y equals arc sine x squared, and we need to differentiate it. We need to find dy dx, and in part A it's telling us to use implicit differentiation, and in part B use the chain rule and a formula for what you get when you differentiate arc sine x. Now there are some results here. Okay, so it's worth learning these results. Right, so let's start by writing y equals arc sine x squared. We'll start by doing the sine to both sides, so we'll have sine y equals x squared. Using the implicit differentiation, because we're differentiating with respect to x, so sine y becomes cos y, but we write dy dx to show that we've differentiated a y term as if it were an x term, and x squared differentiated is 2x. We rearrange to make dy dx the subject, so we'll have 2x over cos y. Now we use the sine squared y plus cos squared y is 1, and then we can use that to change the cos y to 1 minus sine squared y, or the square root of 1 minus sine squared y. So that'll be 1 over square root 1 minus sine squared y. Now we just do the substitution, because at the start here we had that sine y is x squared, so this sine squared will basically become x squared squared, so I'll write that down. So I'll have dy dx equals 1 over 1 minus x squared, which is sine y, but then squared, because it's sine y all squared. So I'd finish off with dy dx is equal to 1 over square root of 1 minus x to the power 4. Now part B, it's telling us to use the chain rule, and the formula for what we get when we differentiate sine x, and that's here, so we're going to use this to help us get the answer. Now I did say that you should remember these results here, but they are in the formula book, so there's no need to really memorize them. So I'll just put down here that these results are in the formula book, so no need to memorize, but if you do remember them, obviously that will save you a little bit of time in the exam. So remember, if we're going to use the chain rule, there's 2 steps. You differentiate the outside, and then multiply by the inside differentiated. Right, so on something like this, the arc sign is the outside and the x squared is the inside. So if we differentiate the outside, which is arc sign becomes this 1 over 1 minus x squared. Now we need to be careful because whatever's here becomes x squared. So if this was arc sine 2x, it will be 2x all squared. Now since we have arc sine x squared, the x that's here needs to get replaced with x squared. So 1 over square root of 1 minus x, which is x squared basically squared. So that's the first bit done. Differentiate by the outside. Differentiate the outside. Now multiply by the inside. Differentiate. The inside is x squared. So we're multiplying by 2x. So we get the same result as before. So 2x over the square root of 1 minus x to the power 4. Now if we want to do it the way where we're using the proper notation, the first thing that we would do, and I'll write this in different colour, we'll say let u equal, or any letter equal x squared. So then we have y equals r sine u. So then we would work out dy du, and dy du using the result would be 1 over the square root of 1 minus u squared. Then we'd also work out du dx, and du dx would be 2x, and since we want to find dy dx is going to equal dy du, or whatever letter you've chosen, times by du dx. So that would give us dy dx equals dy du, which is 1 over 1 minus u squared. Now we'd substitute u squared back here. So u squared is going to be x to the power 4. So 1 minus x to the power 4 times by du dx, which is 2x. So we get the same result as before. So if you want to use the notation, doing the chain rule that way, rather than just my quick hack method, which is differentiate the outside, multiply by the inside differentiated, and you want to use like du dx, do y, and do the chain rule this way, then that's an alternative way to do it using this proper notation. So here it says, given that y equals arctan 1 minus x over 1 plus x, find dy dx. Now I'm going to show you two different ways of doing it, just like we did in the last example. So we will do it by using implicit differentiation over here, and over here we'll do it by using the chain rule. By using the chain rule, it means that we're going to have to refer to one of these results up here to inform the book. So step number 1, let's write this out. Y equals arctan 1 minus x over 1 plus x. Let's get that bracket right. So the first thing that we do is we do tan to both sides. That gets rid of the arctan. So you have tan y equals 1 minus x over 1 plus x. The next step is we're going to differentiate it using implicit differentiation. So tan y differentiated with respect to x from the formula book becomes x squared y, but we write dy dx. I've just differentiated a y term as if it were an x. Then I need to differentiate this part here. Now to do this we need to use the quotient rule. And the quotient rule says that we have u which is the top, 1 minus x. Then we need u dash or du dx, which is negative 1. V is going to be the bottom part of the fraction, the numerator, no, the denominator. So v is 1 plus x. V dash or dv dx is 1. So using a quotient rule, which is, so when we differentiate a quotient like that, we have v u dash minus u v dash over v squared. So let's do that. So that's going to be 1 plus x times by negative 1. So 1 plus x times by negative 1, so I can just put negative outside the bracket, minus uv dash, that's 1 minus x times by 1, so just 1 minus x, all over v squared, so that'd be 1 plus x all squared, like this. We want dy dx to be the subject, so we'll have dy dx equal to, now we can probably tidy up this here, because I'll have negative 1, so I'll have negative 2, and then negative x plus x. So actually all I'm left with is negative 2 over 1 plus x all squared, times by 1 over sec squared y. Now we need to get back in this tan y. Now we've got that identity which says 1 plus tan squared x or y, whatever, is sec squared. So that means I can do 1 plus tan squared y at the bottom. So dy dx equal to minus 2 over this 1 plus x all squared times by 1 over 1 plus tan squared y. Well, tan y is 1 minus x, 1 plus x. So basically I'll replace this tan squared y with this 1 minus x, 1 plus x all squared. So dy dx equals negative 2, 1 plus x all squared times by 1 over 1 plus this fraction all squared, because that's my tan y, like that. Now what we're going to do now is we're going to write this 1 as, let's do it over here, I'm going to write it as 1 plus x all squared over 1 plus x all squared. That will enable me to put these two together, because effectively what I've got here, if I take these brackets out and write it like this, I've got 1 plus minus x squared over 1 plus x squared, and I want to put them together. So dy dx is this minus 2 over 1 plus x all squared times by, it's going to look pretty messy, but we'll tidy up in a minute, 1, which is 1 plus x all squared over 1 plus x all squared plus the bit that was there before, 1 minus x squared over 1 plus x squared. Right, I'll need a bit more space. Let's get rid of that, and we'll carry on with this question over here at the top. Right, so now I can put these two together over the same denominator. So dy dx negative 2 over 1 plus x all squared times by 1 over, and I'll end up with 1 plus x all squared plus 1 minus x all squared all over 1 plus x all squared, common denominator. Now when you divide by like a fraction, we can actually flip it over. So this is the same as multiplying by that bit at the bottom, put at the top. So it now becomes 1 plus x all squared over 1 plus x all squared plus 1 minus x all squared. Now you can see that this cancels out here. So we now have dy dx is negative 2 over this 1 plus x all squared plus 1 minus x all squared. Now the bit at the bottom, if we multiply it all out, we will get from the first bracket x squared plus 2x plus 1. From the second bracket we'll get x squared minus 2x plus 1. I can see that that cancels out. Well, the 2x's cancel out like that. So I'll basically have 2x squared plus 2. So negative 2 over 2x squared plus 2. That will cancel down, leaving me a final answer of dy dx equals negative 1. I'll put negative at the front if I want to, and then x squared plus 1. Okay, so there's my final answer using implicit differentiation. So if you want to have a look at that, you can pause it. I'm now going to do the same question again, but now using the chain rule. Right, so we're going to try the same question, but we're now going to do it using the chain rule, which means we're going to let u equal 1 minus x over 1 plus x, which means we will have y equals arctan u. So we'll need to find du dx, and we use the chain rule to do that. So just a reminder, we said that u was 1 minus x, so u dash is going to be negative 1, v is going to be 1 plus x, so v dash is going to be 1. So du dx will be negative 1 plus x, so that's our vu dash, minus our uv dash, so that's 1 times 1 minus x, all over v dash, v squared, which is 1 plus x all squared. So yeah, just like the previous time, we've used the quotient rule here. So that's du dx. We now want dy du. So we use the standard result up here. So arctan u is going to be 1 over 1 plus u squared. So 1 over 1 plus u squared. We want dy dx, and that's going to be dy du times by du dx. So dy dx is going to be dy du, which is 1 over 1 plus u squared, and we're going to substitute that actually, and substitute the u for 1 minus x over 1 plus x all squared times by du dx, and that's going to be negative, well, we can actually simplify the top, can't we? So let's just write this as 1 plus x all squared. So the top here will be that negative 2, because the x's will cancel out, negative 2. And then the rest of the question is exactly the same as we did previously, so it's just that first part that is any different. Now, is this any easier than the other way? It's probably about the same amount of work, but yeah, the rest of this question I'll probably just write the solution down, but the rest of this is going to be exactly the same as before, so I'm not going to run through all of those steps again. So I'll just put same as previous method, which was the implicit. So we'll end up with the same negative 1 over 1 plus x squared as our final answer for dy dx. Okay, so this is just an alternative way of doing it. So either use implicit differentiation or use the chain rule to get your final answer. You should now be able to do exercise 3C on pages 64 to 65 of the textbook. I've put here the results which you can use, which are in the formula booklet. And remember, with this differentiation, our two main methods are going to be implicit or using the chain rule. So just a quick reminder of both. With implicit differentiation, anytime we differentiate a y term, we need to make sure that we put dy dx after it to show that it's implicit. We're differentiating a y term as if it were an x, so we put the dy dx after it, and then normally after that we make dy dx the subject. With the chain rule, we want to make a function equal to u, so it's normally the bit that's like the function to function, like x squared or something like that. So, and then we'll do we'll work out dy du and then du dx to get dy dx.